Hello everyone, welcome to new class. Today's class is about mechanical rotational systems. The model of rotational mechanical systems can be obtained by using three elements. First one is moment of inertia. J of mass. Second one dashpot with rotational frictional coefficient B and torsional spring with stiffness K. Torsional spring with stiffness K. The weight of the rotational mechanical system is represented by the moment of inertia of the mass, and the moment of inertia of the system or body is considered to be concentrated at the center of gravity of the body. The elastic deformation of the body can be represented by a spring. The friction existing in rotational mechanical system can be represented by the dashpot. The dashpot is a piston rotating inside a cylinder filled with viscous fluid. When a torque is applied to a rotational mechanical system, it is opposed by opposing torques. So there will be opposing torques due to moment of inertia, friction and elasticity of the system. The torques acting on a rotational mechanical body are governed by the Newton's second law of motion for rotational systems. And it states that the sum of torques acting on a body is 0. Sum of torques acting on a body is 0 according to Newton's second law. Or we can say the Newton's second law as the sum of applied torques is equal to the sum of opposing torques on a body. That is sum of applied torques equal to sum of opposing torques. Next is list of symbols used in mechanical rotational systems. So here theta is the angular displacement in radian, d theta by dt is the angular velocity in radian per second, d square theta by dt square is the angular acceleration in radian per second square, t is the applied torque in Newton meter, j is the moment of inertia, unit is kilogram meter square per radian, B is the rotational frictional coefficient, unit Newton meter per radian per second. K is the stiffness of the spring in Newton meter per radian. Next is torque balance equations of idealized elements. So consider an ideal mass element like this. So the opposing torque due to moment of inertia is proportional to the angular acceleration. Let T be the applied torque and Tj be the opposing torque due to moment of inertia of the body. Theta is the angular displacement. So here we can write that is the opposing torque due to the moment of inertia is proportional to the angular acceleration, and that is d square theta by dt square, or we can write it Tj equal to J into d square theta by dt square, where J is the moment of inertia, and by Newton's second law we can write the applied torque is equal to the opposing torque, that is T is equal to Tj equal to J into d square theta by dt square. Next, consider an ideal frictional element dashpot. So let the applied torque be T, then the dashpot will offer an opposing torque which is proportional to the angular velocity of the body, that is Tb is proportional to d theta by dt, or we can write Tb is equal to b into d theta by dt, and by Newton's second law we can write the applied torque T is equal to the opposing torque due to friction Tb, and that is equal to b into d theta by dt. So this is in the case of the ideal rotational dashpot with one end fixed to reference. And next is ideal dashpot with angular displacement at both ends. So this is B. So here we can write Tb is proportional to d by dt of theta 1 minus theta 2, because the opposing torque is proportional to the differential angular velocity. And we can write Tb is equal to b into d by dt of theta 1 minus theta 2, and by Newton's second law T is equal to Tb is equal to b into d by dt of theta 1 minus theta 2. Next, consider the elastic element torsional spring. So here the ideal spring is, this is ideal spring with one end fixed to reference. So here the torsional spring will offer an opposing torque which is proportional to the angular displacement of the body. So we can write Tk is proportional to theta, or Tk is equal to k into theta. By Newton's second law we can write T is equal to Tk equal to k into theta. When the spring has angular displacement at both ends, the opposing torque is proportional to the differential angular displacement, that is Tk is proportional to theta 1 minus theta 2, or we can write Tk is equal to k into theta 1 minus theta 2, and by Newton's second law T is equal to Tk is equal to k into theta 1 minus theta 2. Next is the guideline to determine the transfer function of mechanical rotational system. First one is, in mechanical rotational system, the differential equations governing the system are obtained by writing torque balance equations at nodes in the system. The nodes are meeting points of elements. Generally, the nodes are mass elements with moment of inertia in the system. In some cases, the nodes may be without mass elements. Second one, the angular displacement of the moment of inertia of the masses are assumed as theta 1, theta 2, theta 3, etc. and assign a displacement to each mass. The first derivative of angular displacement is angular velocity, and the second derivative of angular displacement is angular acceleration. Third one is, draw the free body diagrams of the system. The free body diagram is obtained by drawing each moment of inertia of mass separately and then marking all the torques acting on that body. Always the opposing torques act in a direction opposite to the applied torque. Fourth one is, the mass has to rotate in the direction of applied torque. Hence, the angular displacement, velocity and acceleration of mass will be in the direction of the applied torque. If there is no applied torque, then the angular displacement, velocity and acceleration of mass is in a direction opposite to that of opposing torque. Fifth one is for each body diagram, for each free body diagram, write one differential equation by equating the sum of applied torques to the sum of opposing torques. The sixth one is take Laplace transform of differential equation to convert them to algebraic equations. Then rearrange the S domain equations to eliminate the unwanted variables and obtain the relation between output variable and input variable. This ratio is the transfer function of the system. And note that Laplace transform of theta is theta of s. Laplace transform of d theta by dt is s into theta of s. And Laplace transform of d square theta by dt square is s square theta of s. So let us do the problems in the next class. Thank you for watching the class. If you like the classes, please like, share and subscribe my channel.